set up for the current slide. And one announcement that I know, well, two actually. You know about student course evaluations? Were you here to hear me announce it? Okay. Student course evaluations are open now. You probably received a couple of emails. Do you see your Lawson email? You did, okay. Go to your Lawson email, find either of, I think you probably received at least two and maybe more by now, notices about this. And in the text of the email, you'll find a link. Just click on that link. That takes you straight to the survey. And it tells you how to log in, your 7-digit student ID number, numerical digits. That's your login, and your date of your birth, 8 numerical digits. That is your password. And the 8 digits are the first four digits are the year of your birth. It won't be this, but mine would be 1951. And then the next two would be the month of your birth, and if it's a single-digit month, you put a 0. Well, for mine, 01. And then the date of your birth is the last 2 digits. For me, that'd be 07. So if it's a single-digit number, be sure you put a 0 in front of it. Now, you don't have to do these immediately. They will be open through the 8th of August. 8th of August, y'all are going to be long gone. And you're going to be like an Etch-a-Sketch. You've shaken it, and it's completely cleared the memory bank. So don't wait until the 8th of August. Do them while you're thinking about it, okay? You want to do that after you see your final grade, you got time, okay? But please do the student course evaluations. Don't forget. We value them. We really do. I use them for my own self-improvement, but I also use them to evaluate the instructors under me because I'm the department chair. The school uses them. SACS is coming up. They will be looking at them. So please do the student course evaluations. All right, the other announcement. On the syllabus, on my locator card and everything that you've heard and seen me do before, you've probably heard me say my office hours here on this campus, Mondays and Wednesdays pretty slim, 8 to 8:30 and 5:30 to 6. That's all. I'm in class the rest of the day. But on Tuesday and Thursday, much more. 10:45 in the morning until 4:30 in the afternoon, generally on this campus. But the last several Tuesdays and Thursdays, I've had to go to the Birmingham campus for one reason or another, and that's going to continue tomorrow and Tuesday. After that, I hope to be back on my regular schedule being here just about all afternoon. Tomorrow, I'm going to have to leave by 2 o'clock because we've got a meeting at 2:30, and then on Tuesday, I'm probably going to have to leave before 1 o'clock because I've got a hearing at 1:30. So got to be there in time for that. So except for those two and several that we've already had, I'll be here from 10:45 up until when I have to leave. But those leave times have been varying, but after next Tuesday, hopefully they'll be sort of fixed. Any questions on anything we've done so far? And everybody here has the copy of Test 3. All right, we were doing evaluating a definite integral as a limit, which is kind of a real big pain in the neck, but it's necessary, and we got to do it. After this, though, let's see, how many more of these do we have? A few of these to go. Then once we get into 4.4, things get easier. There's some other stuff to do in 4.4, but generally they get easier. This is one of the last ones we have to do with this kind of detail. Here's the definite integral. Integrate from -2 to 1 the function 2x dx. Okay? Now, number one, 2x is integrable everywhere on the real number line. There's no problem with it anywhere. Specifically, it's integral on this interval from -2 to 1. That's what we're interested in. because it's continuous everywhere, including from -2 to 1. Okay? The definition of integrability implies that any partition whose norm approaches 0 can be used to define the limit, and for computational convenience, define the del by subdividing the interval from -2 to 1, okay, into n subintervals, okay, and that will make your delta x, okay, exactly what your delta x. We're going to do them evenly, not like we did on one of the earlier examples. And this will be b minus a, remember that, b minus a divided by n. Well, here your b is 1, so 1 minus a minus 2 divided by n, so that's going to be 1 plus 2 divided by n is 3 divided by n. That's your delta x, okay? And that'll be the delta x for every one of them. Ryan's here. What's that? I don't know. You were supposed to bring them. Why didn't you bring them? Goodness gracious. Okay. Can't, okay. So, now, by choosing a c sub I, now c, remember, is a value within each of the intervals, okay? So you got I intervals, okay? And the c sub I is going to be a value somewhere in that interval, okay? They are using the right endpoints. It really doesn't matter, but by using the right endpoints, you get that c sub I to be, and if you picture this on a number line, let me do one up here, okay? And here's top out part of the alphabet's coming in very strong. Poor old Tariq is holding up the bottom half of the alphabet all by herself. Okay. So, if you picture the number line here, and we're going from -2 to 1, okay? And you're going to split this, and by the way, this 2x is going to go right through this one with a slope of 2, so I'm not going to draw the whole thing because it gets in the way down here. But if you're doing an interval, dx is here, any dx here, then the c value, if it's the right-hand endpoint, will be wherever your a is, that's your -2, so it's a sub 0 plus, and you go over 1, 2, 3, 4, 5, however many I units here, so it's, and each unit is 3 over n, so it's 3 over n times I. That's how far you go over from the first endpoint, which is your -2, and then each interval is 3 over n, and the ith centerpiece, the ith value there, would be 3 over n times I added to the -2, okay? So this would be -2 plus 3 over n I. Remember those good old i's? We got to have them in there. Aren't they fun? Okay. So if you're doing the integral, that's what we're doing, this integral from -2 to 1 of 2x dx, okay? Later we won't do it this way, I promise you, okay? This will be the limit as your norm. That's not the big guy, fat guy that sits at the bar. This is the norm, which is the largest of your subintervals, and they're all the same size. So the magnitude of the norm, as that approaches 0, in other words, your n's getting very, very large, that will be the summation of I equal 1 to n, okay, of your f of c sub I. F evaluated at c sub I, okay? Then multiplied by your delta x sub I. So think of this as Here's your delta x of I. Okay, and this is your value, f of x of I. So you're doing that, the area of that little rectangle, height times width. And you're going to sum all these up. That's what the summation is, from -2 until you reach 1. And that's where n will stop, because you've divided the interval from -2 to 1 into n pieces. So when you get to n, you're at the end there. E-N-D end. All right. Well, what is this? This is the limit. It's tedious, if that's what it says. As your norm approaches 0, which is also as n approaches infinity, you could say it either way, of the summation of I equal 1 to n. That doesn't change. Now, what is your f? Your f up here is your 2x. And your c sub I is this thing right here. So it's 2x evaluated there. So that would be 2 times -2 plus 3 over n I. I don't know where, yuck, okay. All right, times your delta x of I, which is another 3 over n. All right. Now, I probably do this a little differently from the book, and there's nothing wrong with that. And what I'm going to do here, because you see the 2 doesn't have anything to do with the I at all. It's not getting counted, okay? The 3 over n has nothing to do with the counter. So I'm going to take those two pieces that have nothing to do with advancing from I equal 1 to n. I'm going to take those on the outside and make the 6 over n out here, okay? So I'm going to do it here. That would be 6 over n times the limit as the del, the magnitude of the norm, is approaching 0, of what do you have left now? -2 plus 3 over n I. Okay? Let's get, okay. So 6 over n, don't forget, that's there. Okay? Times. Now we're going to break that into two limits. First is going to be the limit as the norm is approaching 0 of -2. Okay? Plus, now I'm going to take the 3 over n out and do the limit as the norm is approaching, I don't know why it's not writing, 0 of I. Okay? Okay. Getting close now, folks. All right. So this will be 6 over n. Don't forget about your 6 over n now. Now, what's the limit of -2 as, I forgot to put my n's on top, didn't I? No, that's right. Okay. I forgot to put my sum in there. That's what I forgot. The sum, as I approaches, goes from 1 to n. Both of these have, I put it outside, but okay, sorry about this. Hold up a minute here. I've just miswritten this really badly. Sorry about this, that you've been copying it down. I got my I's and my limits and my summations crossed up. Okay. There's just one limit here. In fact, I'll put that outside this. Okay. So let me even erase that. Okay. 6 over n times the limit, sorry about that, as the norm is approaching 0 of, now this is what we're taking the limit of. Okay. We're going to break the sum here. See, this is where my problem came. I left off the sum here. I equal 1 to n. Sorry. That's where the error came. Got me all crossed up. Okay. Now, we're going to break that into two sums. The first sum is going to be the summation of I equal 1 to n of -2. plus the next summation. And I'm going to bring the 3 over n outside the summation of I equal 1 to n of I. Okay, so this is 6 over n. Don't forget that's there. Okay, and still need to write my limit. Earlier I was leaving out the sum, this time I'm leaving out the limit. You can tell it's 40 and I don't like doing these things. As the norm approaches 0 of, now let's do these two. What's the summation of -2 as I goes from 1 to n? Sum. That would be -2 plus -2 plus -2 plus -2 plus -2 plus -2 n times. What would that be? -2 times n, right? You do -2 n times, that's -2 times n. That's what multiplication is, right? Repeated addition of the same value over and over and over, that's multiplication. So that would be -2n. Done. Okay? I'm sorry. Yeah. -2 times n. Okay? All right. Now, the second one of these is your plus 3 over, okay. I kind of messed up here too. There's a 3 over n associated with that one too. See, this 3 over n is multiplied by both of those. So this should have had a 3 over n in front here too. Sorry. Because there's 2 3 over n's in there and I messed them up. See, this is multiplied by everything in here. This one's just multiplied by this part. So when I went from this to that, I left off this one too. I left off the summation sign. I also left off the 3 over n. So this 3 over n goes inside the limit, but outside the summation. 3 over n. Left it off there. I put it in one place. Well, I need another brace here because you see there's 2 of them in there. Okay, so I'm going to bring this one 3 over n here. Okay, this is outside both of these. This 3 over n is inside that. Okay, I love doing these if you haven't told by now. Now, what's the summation from of I equal 1 to n of I? In other words, 1 plus 2 plus 3 plus 4 plus 5 plus 6 until you get up to n. Remember what that one was? Good old Gauss or Euler 1. I think it was Gauss. Did this when he was in grammar school. He said it was n times n plus 1 divided by 2. Right? If you go back a few pages, the beginning, when they first started talking about sigma notation, on page 259, you'll see that first one, which is a -2, summation of -2 is just some constant c times n. That's why we said -2 times n. The one that summation of I is n times n plus 1 over 2. That's the second one there. So this is 3 over n times n times n plus 1 over 2. Okay. Now that closes out that one. I need more room. Okay? Seriously in need of room. So I'm going to erase, I think we're through with this now, so I'm going to erase this top line here. And I'll erase my number line up there. I think we've used it for all we can, just so it won't be messy up there, or any messier than anything else ever is. And I'll probably erase that. I'll leave that. Okay. I'll erase that circle there. Okay. Now, whoops. I just erased everything, didn't I? Yay, team. My pen hit the wrong icon down there. So someone fill me in on what we had. We had this integral here to be 6 over n times the summation of n equal 1 to, no, I equal 1 to n, duh, okay, and what do we wind up with? No, see, I'm leaving out my limit again, yeah, okay, it's 4 to n, okay, the limit as your norm is approaching 0 of 6 over n times, oh, no, that's the 3 over n here. That's your delta, no, wait, time out. Sorry. I didn't leave it out, but it's like the 3 over n is incorporated in the 6 over n. So sorry about that. I went back and put it in where I didn't need to. Okay? So I put it in. Yeah, there's 2. One of them's with the 6 over n, and one of them's with that second, with the other part. Oh, yeah, but there is a, okay. You're right. It still goes here. This is the second 3 over n. No, it's not. I'm right in the middle of.
You can just start over.
Do I really want to? No. Okay. Let me pick up right where we were. Here's where we were. I think I was down this far. I'm going to write the previous line. The 6 over n. Now, I do see something. Because the n is involved with this needs to go inside the limit. Outside the summation, but inside the limit. 6 over n, okay? And then your summations, that's where it goes. I'm going to write the previous one that I know I had there. Okay. Now, they're doing it slightly differently. Well, we did it. It's -2 times n, okay? That part we had. Now, this part is the second 3 over n. 3 over n, okay, times n plus 1 over 2. That was that second part. That was the summation of I from n equal, I equal 1 to n. Okay, so what does that give us? This gives us the limit as n, okay. All right. I've been saying this, the book changed it. Your norm going from to 0 is the same as n going to infinity. Because as the maximum partition is going to 0, that means your n has to be getting bigger and bigger and bigger. Because remember, the norm, the del, is that good old 3 over n, okay? As that's getting closer to 0, that means n is getting closer, is going to infinity. So they changed the limit here to n going to infinity. I've been saying it, they actually made the change, okay? Now, of 6 over n times -2n plus 3, I'm going to multiply all these things together. 3n squared plus 3n times 1, and both of these are over 2n. All right? All right. Now the limit of that as n is approaching infinity, that's supposed to be an n, not an h, of, let's multiply through, that'd be -12 over 12n over n plus, now multiply this n times that, and you get 2n squared in the denominator, so you have 3n squared plus 3n over 2n squared, because this n times 2n is 2n squared. All right? Now, before we take the limit, notice that these n's go out, and yeah, let's rewrite this as the limit as n goes to infinity of minus 12. That's just there. The n's disappeared. And let's split this one plus 3n squared over 2n squared. That's an ugly n. Plus 3n over 2n squared. Okay, what I did is just break up this into two fractions. Okay? Now, here the n squareds go away, and here one of the n's goes away. Only one. Okay?
Weren't you supposed to multiply it by 6?
I'm sorry?
The numerator, weren't you supposed to multiply that by 6?
You're right. I forgot. That goes here too. So 6 times 3 is 18, and this will be an 18. See how easily that I forged that? Okay. Isn't that nice? Okay. Absolutely right there. Okay, so what do these become? The limit as n goes to infinity. Well, the only n you have left is this one, and as n goes to infinity, 18 over 2n, that goes to 0. Because if you get a fixed number over something that's getting very, 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 very large, that's going to 0. Okay? So what do we have left? We have minus 12 plus 9. And that had better equal negative 3. Perfect. Sorry about that. Okay. Now that's the definite integral. Now we probably, if you think back on it, you're probably not too used to having negative answers for integrals. There's nothing wrong with that. When we were defining the integral as an area, but keeping the function above the x-axis, they were always positive. But this one isn't above the x-axis. At minus 2, this is down here at minus 4. And it's going up to plus 2 here. So most of the time it's negative, just a little bit of the time it's positive. So that's why you wind up having a negative area. Because this part is counted as a negative number, that part's counted as a positive number. So don't sweat, don't worry about having negative integrals.
This says 18n squared.
Yeah, 18n squared over 2n squared. The n squareds go away. 18 over 2 is not.
Okay, what about to the left?
The next one is n over n squared. 18n over 2n squared.
So wouldn't it be 9 over n?
Okay? That would be 9 over n. You're absolutely right. Okay? You're absolutely right. I skipped that step. 9 over n. And what's happening to that is n is approaching infinity. 9 over 1,000,000. It's a pretty small number, right? 9 over 350 million. Even a smaller number, right? And that's getting closer and closer to 0, right? So as n is going to infinity, 9 over n is going to 0. So I just left it 18 over 2n over 2n. Yeah, that's going to 0 too.
I'm talking about
The one
to
right
left,
here?
To left.
Right
To
here?
left.
This one?
Okay, to left.
This one?
Yeah, there you go.
Oh, okay. What I did here, this part stayed the same except I canceled out my n's. This part became 18 n squared over 2n squared, which I could have written as 9n squared over n squared, right? Okay, I just left the 18 over 2 and changed the 9 down here. But the n squares cancel out there. And then this one is plus 18n over 2n squared, which I wrote here, which I could have written as 9 over n. You're absolutely right. Okay? This is the myriad, right? some help with the bottom part of the after that now. All right. So that gave us -3. So what they say here, because the definite integral in example 2 is negative, it does not represent an area of a region, because areas by definition are not negative, okay? Definite integrals can be positive, negative, or 0, okay? For an integral to be interpreted as area, the function f must be continuous and non-negative on a to b. This one wasn't, so this isn't interpreted as an area. And that leads, oh wait, let's see how they did the problem. I'm sorry, I should have erased this earlier before I started reading that. So let me go back. Because the function f of x is equal to 2x is integrable on the interval from -2 to 1, because it's continuous, because it is continuous on -2 to 1. In fact, it's continuous everywhere. It's a polynomial function. Continuous everywhere, specifically -2 to 1. So therefore, it's integrable on -2 to 1, as it is everywhere. Okay, moreover, the definition of integrability implies that any partition whose norm approaches 0 can be used to determine the limit. So why not use the simplest one? Okay, we'll use this good old norm here, our definition for your delta x of I to be, all your delta x's, not just the item, but every one of them will be b minus a, which is 1 minus a -2 divided by n, that's 3 divided by n. That's every interval, and that's your delta x in general. Okay? And that's the norm is going to be that too, because that's always going to be the same. Okay? By choosing c sub I as the right endpoint. Now, the only difference that makes is how we define this. Okay? So the right endpoint would then be the a, which is your first one, plus I times delta x. So you're on the right endpoint, you go over 1 delta x unit here, 1 plus 3, I plus 3 over n, that'll be the right endpoint. And then to go over the next one would be 2 times that delta x, so 2 delta x's, okay? 2 times 3 over n. The next one would be 3 times the other. So you keep on going until you get to the nth one will then be your b, which is your 1, way out there. Okay? Now, what this c sub I is then, your a is -2, and your I times delta x is this I times this delta x, 3i over n. Okay, so that's your c sub I. Now, remember what your summation, okay, here's your definite integral. The integral from -2 to 1 of 2x, that's your integrand, that's the thing you're doing, the function, times dx, okay? Now this integral stands for a summation, but it's a limit of a summation. So the limit goes first. The limit as that norm, the largest of those increments, but they're all the same, is approaching 0, of the summation, that's what the integral is, from I equal 1 to n, of your f sub c I, this is your 2 times c I, times delta x I. That's your dx. So you see this is your function, that's your dx. This is your sum. This is what this does, only this is the limit. That takes this to d, rather than being a delta, it goes to d, and it takes the sum to be an integral. Okay? So if you plug that in, now, here's where they made their change. They went from the the norm, going to 0, to n going to infinity. Because as the maximum length of that thing goes closer and closer to 0, that's what this is saying, that means your n has to be going to infinity. Because over n, that makes that go to infinity. Okay? So this will be summation of I equal 1 to n of f sub c sub I. We already know what c is, that's from the previous slide, and we know what the delta x is, that's from the previous slide. Now, is there any reason they dropped the I there? No, I don't think they should have. They did in the book as well. But you remember, the delta x of I is just your delta x. So that's why they did it, I assume. You could have left it or not. It doesn't matter. Now, that's the limit as n goes to infinity of the summation I equal 1 to n. That stays the same. Now, what is this alpha c? It's 2 times your c sub I. And from the previous slide, the c sub I was negative 2 plus 3i over n. And then your delta x is 3 over n. Okay, so we were with them down to here, and I sort of got all screwed up after that. What matters in the summation are your i's, okay? So any multiple that does nothing to do with I, like this 2, no, it can come out. The 3 over n, that's just a constant. That can come out. It comes outside the summation. I like to go and get it outside there, okay? Now, it can't go outside the limit because the n is going to infinity, and these both, or this one at least has an n in it. But this one has an I, and this is a term that is going to be counted over and over and over again. The 2 times and the 3, they can come out, okay? 2 and the 3 over n can come out. So that's why I pulled those out, and that sort of screwed me up, but I wasn't paying. Yeah, they did it too. See? They pulled the 6 over n outside here, inside the limit, but outside of the summation. So now you do this, and all you're summing is your negative 2 and your 3i over n. Of course, you have to sum that. Okay? Now, the next step, they're going to use the rules for, it's really, just like they pulled the 6 over n outside the first part of the summation, they're going to pull the negative 2 out of this one, okay? And now you're just summing n equal, I equal 1 to n 1. So it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 up to n. So it's just going to be n. Huh? Okay, and then times the negative 2 on the outside. Yeah. You can just pull the negative 2 out, just like we pulled the 6 over n out, but this one you just pull out of this one. It's not in that one, so you can't. Okay? And then the next part of it, the 3 over n, this 3 over n, the one that was with the side, it can come out of that one in the summation I equal 1 to n of I. Okay? Now this we know to be n, this we know to be n times n plus 1 over 2. So that's what we're going to do next.
You said we know the 1 to be what?
1, okay, the summation of 1 from I equal 1 to n. That'd be 1 plus 1 plus 1 plus 1 plus 1 n times. That's going to be n, right? 1 times negative 2, so that gives you negative 2n. Okay, then the 3 over n is outside this, and then that summation, you can go back to that earlier table, or check with Waller or Gauss, whoever it was that did it, and he came up with this, or many others have, n times n plus 1 over 2. That's the summation of I equal 1 to n. Go back, it's one of the properties, okay? That's what it is. Okay. Now, what we do before we take the limit is multiply. This is where you have to be careful. Distribute this across this part, this across both parts, okay? So what do we get? The limit as n goes to infinity of, and they just get many steps here. 6 over n times negative 2n. 6 times negative 2 is negative 12. N over n is 1. That's done. Don't forget, as I forgot and Patrick pointed out, the 6 over n is multiplied by this as well. So this would be 18.
Don't you want to multiply 3n and whatever that is together first before you multiply it?
Okay, you have to speak a little louder, I'm sorry.
I said, once you want to go ahead and multiply 3n times whatever that is.
That's exactly. I say show more cells. They just went from this to that without showing. So that's what I'm trying to describe. So let's do that, what you just said. 3 times n is 3n times n is 3n squared over 2n. Okay? And then this would be 3 times n times 1. That would be 3n over 2n. All right? So, all right. Now, multiply both of those by 6 over n. So this is 18 of it. And this is
18n squared and
18n squared plus 18n all over 2n squared. Okay? So 18n squared over 2n squared is 9. And 18n over 2n squared is 9 over n. Yeah. Yeah. And that's, we did that part. Now, as n goes to infinity, that goes to 0. Because 9 over n is going to get bigger and bigger and bigger. It's closer and closer to 0. So that's going to 0. That leaves you negative 3. Which is what we finally got. Okay. The hard way to do the problem, okay? But this is using limits. That was the title of this thing. Remember? Riemann sums, evaluating a definite integral as a limit. Please don't make me do this the rest of my life, okay? I'll become a music major or something rather than do this the rest. No, I'm just kidding. Nothing against music majors, okay? But I can't sing, I can't play, I can't do anything. I'd rather do that than have to do Riemann sums the rest of my life, okay? There is an easier way. But here's what they were talking about before. Because the definite integral in example 2 is negative, that answer was negative 3, it does not represent an area of a region shown here. Or it really does, sort of. Okay, I'll put that in. Because this area down here, because it's below the x-axis, that is actually a negative value. Okay? And this is a positive value, and the sum of those is a negative 3. But we don't usually talk about areas as being negative. So that's what they're saying. Definite integrals can be positive, they can be negative, or they can be 0. They don't have to represent an area, especially if the function is below the x-axis. For a definite area integral to be interpreted as an area, the function f must be continuous and non-negative on the interval a to b. If it goes negative, it's no longer an area. It's a difference in two areas. Okay. It's stated in the next theorem, and here's the next theorem. The definite integral is area of a region. If f is continuous, always had to be continuous, and non-negative on a closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equal a to x equal b is exactly that. Okay? That's what they mean. The area, as long as this is not negative. We've seen this picture before, remember a little earlier. And I said then, you can't send the a back here because the function goes negative here. As long as the a is in the function's positive above this and never goes negative, then that is the area. Sorry?
What's the real application of integrals?
Okay, one more.
I said, what's the real life application of integrals?
Of an integral?
Yeah.
Boy, there's tons of them. If you're trying to calculate a displacement given an acceleration, you integrate, you integrate, you integrate. Okay? You do it twice, actually. Okay? There's just lots of others. If you're trying to find out if this is your profit for your business over a 12-month period, the summation of that is what you made in a year. Okay? It's the integral of that. The area under a curve, as long as it's positive, the curve is always positive, that gives you a valuable piece of information.
If it was negative, wouldn't that be like debt?
Then you would have a deficit. Then you have a loss. So your net profit would be like we just had. And if that was your profit line and you had way more up here than here, over that year you lost money. Okay? So that's the thing. So yeah, it would still work then, but then it would not be how much you made, it's how much you lost, not how much you made. Okay? You lost a negative. You made a negative amount. So anyway, you can use a definite integral to find the area of a region bounded by the graph of F, the x-axis, x equal A to x equal B. Okay, later we're going to extend this to two functions, and then either one of them can be negative. Okay, but we'll get there in a minute, or in a little bit. As an example of theorem 4.5, consider a region bounded by the graph of alpha of x is equal to 4x minus x squared. The x-axis is shown here in this figure. Okay? Now, notice they didn't give you the A and B this time. They say, what is the area bounded by this curve? So what you have to do is figure out where this curve goes to 0. So you set that equal to 0, and then of course you can you can factor that to be 4x, x times 4 minus x, right? So either x equals 0 or x equals 4. That gives you the limits here, okay, where they're 0. Everywhere in between that, they're positive, okay? Anywhere beyond that, they're negative, so you don't count that. The area bounded by this curve in the x-axis will go from 0 to 4. And that's exactly how they get the limits there. Because f is continuous and non-negative on the closed interval from 0 to 4, from here to there. Then you just integrate from that part. That gives you an area. This part down here would not give you the area bounded by that curve. Okay? Make sense? Sort of? A little bit? Okay. Any question? Okay. You can evaluate a definite integral in two ways. You can use the limit definition if you're really that much of a glutton for punishment, or you can check to see whether the definite integral represents the area of a common geometric region, such as a rectangle, a triangle, or a semicircle. Who is? If that's all we had, we'd still be hurt. Okay? So here's a few. Sketch the region corresponding to each definite integral. What would this be? F of x equals 4. Describe to me what that would be. Horizontal line, 4 units up, right? And if you're going from x equal 1 to x equal 3, it's 4 units high. How wide is that? From 1 to 3. 2. 2 times 4 is 8. You don't have to do a Riemann sum with that. Please don't. You can just look at it and see. Okay? How about this? X plus 2. Okay? Here's what we're going to do. I don't like graphing, but boy, it's better than Riemann sums, isn't it? I didn't say that, did I? Okay. All right. How would this look? X plus 2. What's the y-intercept? 2. What's the slope? 1. Okay. So it'd be going something about like this. And we're going from 0 to 1, 2, 3. Somewhere up here that would be 3, 4, 5. Okay? So that would be this area right here. Now, this happens to go out here to minus 2, by the way. Minus 1, minus 2. Okay? Because when x equals minus 2, this equals 0, so you're out here. So that's a triangle with this part cut off. So what's your base of this bigger triangle? This, by the way, is 3, right? This is 2, 3, 4, and 5. This is 1, okay. So what's the area of the bigger triangle? What's this base? 5. Its height? 5. 5 by 5 is 25, and half of that would be 12 and a half. So this would be the area of this big part is 12 and a half. Now let's take this little triangle. What's its base? 2. Its height? 2. 2 by 2 is 4, and half of that is 2. So 12 and a half minus 2 would be 10 and a half. So that should be the area there. Okay? That's
Yeah, that's right too. They got 21.
what they get.
21 on 2.
Okay, which I believe is pretty close to 10 and a half, isn't it? Yeah. Okay. Now, I guess I should have done this. The first one we did was constant 4. Width, that's the height. The width was 2 from 1 to 3. So that area is 8. Don't do a Riemann sum if you can help it. I'm sorry, I didn't say that, did I? Okay, the next is a trapezoid. Now, I did it one way. They're doing it a different way as a trapezoid. I didn't know if y'all remember what the area of a trapezoid was, but that would be 1/2 the sum of the two sides here, which is 2 plus 5. 2 plus 5 is 7, right? And half of that is 3.5 times 3. 10.5. Okay? We got it a different way, but they got 21 halves. Okay? 1/2 of 3 at your base here times the sum of the others. 7. And that's 21 halves, which is 10.5. Okay? Now let's see the third one. Let's go back to here and we'll do, ooh, will we? Are we going to do that one? I think we will. Okay? Let's erase all that ink. What does that graph as?
Oh, that's the house.
It's a what?
Half of it.
Half of the circle, is that what you said? It's exactly right. Its radius is 2. That's a pretty ugly half circle, but forgive me. So the radius is 2. What is the area of a full circle? Anyone know?
Half time based on height.
Pi, say again? Pi r squared. I always thought pi were round, but no, pi r squared. No, I'm just kidding. Okay, pi r squared, and r is what? In this one? 2, and r squared would then be? 4, so 4 pi would be the area of the full circle. This is only half of it, so what would that be? 2 pi. So we think the area here is 2 pi. All right, let's see what we get here. Oh, well, that's what they're going to do. Okay, yeah, they get 2 pi. All right. We'll find another way to do this without having to do geometric figures either. Because geometric figures, there's very few of them that work. Okay, like that trapezoid. I mean, not trapezoid, parabola. You got to get into some deeper math to get that area. Okay. So sure enough, that gave you 2 pi. Now, the variable of integration in a definite integral is sometimes called a dummy variable. That's really bad for them to call them names like that, isn't it? No, okay. Because it gets integrated away. It's replaced by any other variable without changing the value of the integral. And yet it was the independent variable, okay? So you see the integral from 0 to 3 of x plus 2 dx, which we just did, is the same as the integral from 0 to 3 of t plus 2 dt. Doesn't matter as long as that and that are the same values, it's the same integral, okay? So it doesn't matter what you call it. They have the same value. That's why they call it sort of the dummy variable. Now, on an indefinite integral, you can't do that. I mean, that value stays with you. But on a definite integral, you lose it anyway. You just get a number. Okay? Now, let me make sure that I'm not skipping anything. No, I don't think so. Okay? Properties of definite integrals. The definition of a definite integral of f on the integral from interval from a to b specifies that a always has to be less than b. You don't go from here to here, you go from here to here, left to right, okay? Now, however, it is convenient to extend the definition to cover cases which either a is equal to b or a is greater than b, okay? It's going to be a little bizarre, but let's think it through. Geometrically, the next two definitions seem reasonable, and they turn out being reasonable. if A is equal to B, if your starting point is equal to your ending point, what are you measuring? The area of a straight line. Guess what the area of a line is that has no thickness? 0. Okay? So that's going to be the first one. Now, what if A is greater than B? You're going from here to here rather than here to there. Well, you're going backwards, so maybe it makes sense for that to be negative. And indeed, you'll see that's the case. For instance, it makes sense to define the area of a region of 0 width, which is a single line where A is equal to B, and a finite height to be 0. And that's exactly what we do. And here are those two definitions of special integrals. If f is defined at A, x equal A, and the integral from A to A, you're not going anywhere, you're right there at A, of f of x, whatever that value is, the dx is 0. So whatever this is, even if that was 3 million, 3 million times 0 is still 0. Okay? Because your beginning and end point, you haven't gone anywhere. Now, if f is integrable on A to B, then, now this time, when they put A down here, that has to be the lower value, lesser value. Now, I can't remember if it's this class or my Cal 2 class. A bunch of people did an interval from infinity to minus infinity. Well, I knew what they were talking about, but that's not how you write it. It always goes negative to positive, or lower number to higher number. Intervals go left to right. So this implies that A has to be less than, or I guess equal to B, but it can't be greater than B, if that's the interval. Okay? Then this integral from B to A, which doesn't make sense, the bigger number to the smaller number, that's going backwards, so that's the opposite of the integral from A to B of f of x dx. So yeah, hopefully this sort of makes sense. If you're going this way, it's a positive interval. If you're going that way, it's a negative interval. Okay? Make sense? All right. So let's do a few of those. What do you think the definite integral from pi to pi of sine of x dx? 0. It's got to be. Okay? Now, how about that one? 0 to 3 of x plus 2 dx. And didn't we just do that one? Second, it's a trapezoid, and remember what its area was?
1/2 times
10
10 and a half. It was 21 halves or 10 and a half. So that would be minus 21 halves. If you do it backwards, that's going to be a negative of that. Okay. Good deal. Y'all were quick on that one. So let me erase this. And because the sine function is defined at x equal pi, the upper and lower limits are equal, you can write that's equal to 0 because your dx is 0. There's no change between pi and pi. Okay? And then on the second one, that is the same as given in 3b, except that the upper and lower limits are interchanged. So to flip them back, you negate it, and then we already know the value of that was 10 halves, or so 20, yeah, 21, negative 21 halves, 10 and a half, negative 10 and a half. Okay. I'm sorry? Those are easy ones?
Yeah, they always do the example.
Oh, yeah, of course they do. That's their practice. Okay. All right. Okay. Now, next thing we're going to do is this one. In this figure, the larger region from A to B can be separated into this piece plus that piece. Okay? Can be divided at x equals c, as long as c is somewhere between A and B. Okay? Into two subregions whose intersection is a single line segment. That's the intersection of those two. Okay? A single line segment. Because the line segment has a 0 area, it follows that you can do the area, the area of the bigger one here, this, is the sum of the areas of this one and that. Well, of course, that looks like it makes perfect sense. So that the integral from a to b of f of x dx, which is the whole area under here, would be the integral from a to c of f of x dx, which would be this integral, this area, plus the integral from c to b of f of x, which would be this area, and these two add to do the same as that. So hopefully that makes perfect sense. How's the line segment? Okay, we already said that. So here's the theorem. If f is integrable over 3 close intervals determined by a, b, and c, and if defined like that, see the figure, then the integral from a to b of f of x dx is the same as, is equal to the sum of the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now don't worry about letters in the alphabet getting out of order. It's where they fall on the number line. If c is to the left of b, then this is the lesser number. Don't think just because c is beyond b in the alphabet, it has to be beyond b on the number line. It's not. It's over here, so the integral from c to b, that's a positive integral. So don't worry about the letter spacing. Okay. All right. So here's example 5, and again, a fairly easy one. Okay. But this is a function that's not a very easy one. Okay? Here's law. Okay. All right. The integral of absolute value of x dx from -1 to 1. Oh, man. That's sort of a pain in the neck, isn't it? Because the absolute value of x is not a... Remember when we were doing antiderivatives? It's not a smooth function, so you can't do the antiderivative as is. But you can split it into 2 pieces, because the definition of absolute value of x, when x is negative, that's the minus of x. So anywhere from -1 to 0, that's minus it, the integral of minus x dx. And when it's positive, it's just x. So that's the integral from 0 to 1 of x. So, because, okay, give me a number, any number. 5. What's its absolute value? 5. Give me a negative number, any negative number. Negative what? 23. What's its absolute value? Did you say something? I can hear. 23, exactly. So the definition of an absolute value is the opposite of the number if the number is negative. Like negative 23, its opposite would be 23. But if the number is positive, it'd just be the number. So this is the definition of absolute value. It's minus x anytime x is negative. It's x anytime x is positive. Okay? So then split this into 2 integrals. Integral from -1 to 0 of minus x dx, and then the integral from 0 to 1 of x dx. Okay? Now both of those produce little triangles, right? And they don't show you how they got it, which is a shame. They should have, but they didn't. Here is, and you really don't need this anyway, but here is the absolute value. Okay, -1, 1, 1. Okay, it always forms a V, right? And the area here, that's exactly a triangle whose base is how much? 1. And its height is 1. So 1/2 the base times the height would be 1/2, right? 1 by 1 is 1, half of that is 1/2. Over here, the base is 1, the height is 1, and 1/2 the base times the height would be 1/2. You add 1/2 to 1/2 and you get 1. Almost a duh, but not quite. Okay. So, second? Yeah. And here's Malcolm. All right. All right. Let's see how they did it. See, I don't see why you even had to write that out, but they did. Okay. You could have just drawn the absolute value and done the areas under the curve. But let's erase that and see how they did it. Oh, wow, 1/2 plus 1/2. They didn't show a thing, okay? And that's equal to 1. Without showing any drawing or anything else, they just say 1/2 plus 1/2 is 1. You have to take their word for it. That's what it is. Drives me a little crazy sometimes. So here are some other properties of definite integrals. If f and g are both integrable on some interval a to b, and k is any old constant, big, small, whatever, positive, negative, whatever, fraction, decimal, whatever, rational, irrational, whatever, it doesn't matter, any old constant, then the functions kf and f plus or minus g are both also integrable. This is basically your linearity principle here, or property of integration. So if you have a constant times an integral of times a function, pull the constant outside, okay? Just integrate the function and then multiply that result by the constant, okay? Or if you have the sum or the difference of two integrable functions, and that makes a big mess, then just separate them. Do the integral of the first, plus or minus, keep the sign the same, the integral of the second, and you can do it that way. If that's easier to do it that way. If this is easier to do it this way, okay? Note that the property 2 of this theorem can be extended to cover any finite number of functions. So if you had f of x plus or minus g of x plus or minus h of x plus or minus k of x plus or minus, and you just had a whole bunch of them, you could split them up into the individual intervals. Okay? If it takes more effort to add them together first or subtract them from each other, and you want to just integrate them separately, integrate them separately. All right. Then there's one more property that we're going to, oh, no. Oh, I'm sorry, I missed example 6. Here's example 6. Says, evaluate that, and they tell us the answer, and this is really a big pain in the neck, but they do it, and it's fine. We'll take their word for it. Okay. Well, here's what we have. The integral from 1 to 3 of minus x squared plus 4x minus 3 dx. Well, from our last thing here, when you have a sum or a difference, split them up. Okay? So this will be the integral from 1 to 3 of, I'm going to pull the minus on the outside, x squared. That's from both the first property where k was minus 1 and the second property when we just pulled them apart. Okay? Dx. What do you think will go next? I'll even put the sign for you. Plus 4 times the integral of x dx. And guess what goes next? Minus 3 times the integral of dx. Okay? Now, all these are evaluated from 1 to 3. From 1 to 3. Okay? Now, they told you what this one is, so what would that be? You have the minus sign out here. Not minus 26 over 3. Because this integral right there is that one, right? But you got a minus sign in front of it. And then what do we do next? Plus 4 times 4 minus 3 times 2. Okay? Well, this is minus 26 thirds, one of my favorite numbers of all time, plus 16 minus 6. So that, to me, looks a lot like 10 minus 26 thirds. I'm going to rewrite that as 30 thirds. Isn't that 10? Yay or nay? Yeah. Minus 26 thirds. And that's going to be, help me somebody, 4 thirds. Okay. And I think that's what they got to. Now, I don't want to say these kind of things are sort of worthless, but once we do what we're going to be doing later, this seems sort of almost silly to have done. But the principle is there, and they're trying to define it. The solution here, you break that integral into, and now they show lots of steps, okay? The integral of minus x squared from 1 to 3 dx plus the integral from 1 to 3 of 4x dx minus, plus the integral from minus 3 from, and here's, okay, top part of the alphabet pulling ahead again, way ahead, bottom part hanging in there, okay. Now, that did what they used there was this principle back, oops, that principle here, number 2. They just split that in individual integrals, okay? So what they're going to do now is the part 1. They're going to pull out the constants, okay? So let's go back and see how they do that. Oh, wait, I went too fast. Okay, so how are they going to do that? Here are the constants of minus 1. Here's the constants of plus 4. Here's the constants of minus 3. So they're going to pull those out. So you have a minus 1 times the integral of x squared dx, which they told us what that value was, plus 4 times the integral of x dx, which they told you that value, and then minus 3 times the integral of dx, which they told you that value as well. So now we just substitute those values in, keeping the things in front, minus 26 thirds, plus 4 times 4, minus 3 times 2, and that came up being 4 thirds. They didn't show us how they got that. They just magically got 4 thirds, which is the same thing we got when I showed you how to do it. Make sense? Okay. So rather than you have to come up with geometric shapes, which would be really hard here, they just tell you what those are. And now there's just one more thing. Sort of what I was hinting at before. If f and g are continuous on a closed interval of a to b, and 0 is always less than or equal to f, and f is always less than or equal to g, for all the x's on that interval a to b, then the following properties are true. So here's your f, it's always greater than 0. Here's your g, it's always greater than f. Okay? First, the area of the region bounded by the graph of f and the x-axis has to be non-negative because we said f is continuous and f is greater than 0. So that has to be non-negative. Okay? Second, that area must be less than or equal to the area of the region bounded by the graph of g because g was greater than f everywhere, so the area's got to be greater everywhere or equal. Okay? So this then leads to something else. If f is less than g, then the integral of f in the same region, everywhere in that region, f is less than g, then the integral, or the area under f, has to be less than or equal to the area under g. It's got to be. There's no way around it. If g is always greater than or equal to f, then the area under f has to be less than the area under g. And that's given in this theorem. Preservation of inequality, if f is integrable and non-negative on a closed interval a to b, then 0 is less than or equal to the integral of f to b, because f is integrable and non-negative, so it has to be greater than or equal to 0. And if f and g are integral on a closed interval, a to b, so f is always less than or equal to g for every x on that interval, then the integral of f of x has to be less than or equal to the interval of g of x. The area under has to be less. Okay, that does finish the section 4.3. Homework exercises here would be number 3, which is both at Calc Chat and Calc View. Any of the odds 5 through 9, they're all at Calc Chat. 7's at Calc View. 11 is at Calc Chat. Any of the odds 13 through 21, they're all at Calc Chat. Okay. Any of the odds 23 to 31, they're all at Calc Chat. 25's at Calc View. Any of the odds 33 to 39, they're all at Calc Chat. 37's at Calc View. Then you can do either 41 or 43, they're both at Calc Chat. 45's at Calc Chat. You can think about doing 47. Sort of an interesting problem. It should be at Calc Chat. You can think about doing 49 and or 51. They should both be at Calc Chat. And you can explore doing 53. It should be at Calc Chat. And verifying a rule 55 should be at Calc Chat. And using some different methods, 57 should be at Calc Chat. Then any of the odds 59 to 61 should all be at 59 or 61 should be at Calc Chat. True false 63 through 67 should be at Calc Chat. 69 should be at Calc Chat. Then there's a proof 71. If you're interested in doing that, it should be at Calc Chat. You can think about doing 73. It should be at Calc Chat. 75 should be at Calc Chat. Think about doing 77. It's at Calc Chat. Or 79. It should be at Calc Chat. Okay. You don't have to do all those, but any of those that expand your understanding of what we're doing. So let's discard that and move on to section 4.4. What's that again? I think so, yeah. Okay, now, we're awfully close to where we usually take a break. Do you want to take one here since we're changing sections here? Or you want to keep trucking? Break or no break? That means no break? Okay, when you shake your head, it does mean no break, and you shake your head. No, okay. You want a break or not? Not? Is that what I heard? Okay, keep trucking. Is what you're saying? Okay. That's surprising. Anyone need a break? If you do, it's a good time for one before we start this. But no one does. Speak up. I mean, don't be shy. No one wants a break. Okay. Get set up. Actually, I would like one. Okay. So, all right, well, it's still coming into focus. So several people came in since I made the announcement at the beginning of class. Let me make it again. Have all of you done your student course evaluations yet? Probably not, but you don't have to do them yet. But please don't forget to do them, okay? They're very valuable to us, to me and to others. All right, so let's continue in chapter, well, let's go from current slide. And this will be going from chapter 4, integration. 4.4 is the fundamental theorem of calculus, and most books have a part 1 and part 2. This one calls it a little bit differently, but we'll get to that. Okay? Evaluate and a definite integral using the fundamental theorem of calculus. If you do enough of those Riemann sums, you will love this, okay? That means you don't have to. Let's understand and use the mean value theorem for integrals, okay? We'll find an average value of a function over a closed interval. We'll understand, you will understand, and use the second fundamental theorem of calculus, what other books call part 1 and part 2, this calls fundamental theorem and second fundamental theorem. Sort of same thing. Understand and use the net change theorem. Are there more? Nope. First, fundamental theorem of calculus. You have now been introduced to the two major branches of calculus, differential calculus, integral calculus. But at this point, these two problems seem unrelated. But there's a very, very close connection. Now, they go into a little more too much detail here about giving these, but they do give them, okay? The connection was discovered independently by Isaac Newton and by Gottfried Leibniz, or at least they claim they discovered it independently, and is stated in the fundamental theorem of calculus. Now, before we do this, let me flash back into time here. Back when you were way, way elementary, possibly kindergarten, but early elementary, what's the first operation you ever learned in math? Say again? Addition. And you probably struggled, to memorize all those things, did all those right. We thought, whew, I finally have this done. Then they turned around and did what to you? Made you subtract, which undid the addition, right? And nowadays we call those inverse operations of each other. And then you thought, well, I finally got that done. And then they sprung on you multiplication. And you had to learn all those multiplication tables and stuff like that. Oh, that was fun, wasn't it? And then you thought, finally I finished and got all this done. And then they had you do what? Undo it with division. Another inverse operation. Okay? Now, sometime much, much later, you probably learned how to raise things to powers. Okay? You got that done. And then they taught you how to undo that with taking roots. Another inverse operation. Okay? Since then, we've learned about functions having inverses, like the inverse of a sine is the inverse sine, or the arc sine. You did that in trig, didn't you? Okay? Also, the exponential function has an inverse function, the log. So, a lot of functions, if they're one-to-one functions, they have inverses. Okay? One undoes the others. Now we've got branches of calculus, and we're going to learn that they're inverse procedures of each other. Informally, the theorem states that differentiation and definite integration are inverse operations. Inverse operations, one undoes the other in the same sense that division and multiplication are inverse operations. To see how Newton and Leibniz might have anticipated this relationship, now this leaves to me a little to be desired, but if it speaks to you, then let's do it, okay? Consider these approximations shown here, okay? When we were doing our differentiation, we started with a secant line, and we talked about the slope of that secant line, and then we let the delta x get smaller and smaller and smaller until it became a tangent line, all right? Now, okay, here we have a function here, and we have the area under the function. We also have the area of the whole rectangle here. And the area of the rectangle is delta y by delta x, okay? And they don't really show how you get this. This leaves me hanging really badly, okay? But definite integration gives the region under the curve, okay? And they do that by another process of a delta y, delta x, that's your things here, and the delta y would be the different values here. I wouldn't call that a delta y, but anyway, that's what they do. So to me, this is really, this makes sense. I really can't quite follow their logic there, but they are definitely inverse operations in a sense. Well, here's what they're saying. Well, no, it's not what they're saying. This is the division sense. That's the multiplication. That's the best thing I can get out of what Betsy's showing. This makes sense. I really don't understand for sure what they're getting at there, except that this is a ratio, a division, and that's a multiplication. Multiply an area times a length times a width. Okay? That's the closest I can get out of that. The slope of the tangent line was defined as the quotient delta y over delta x, which is the slope of the secant line, but then you let the delta x get smaller and smaller and smaller. Similarly, the area under a region under a curve was defined using the product of a height times a width. Now that's a y times a delta x. That's the area of a rectangle. I don't count that as a delta y. I count it as a y times delta x. Okay? So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to be sort of the same inverse relationship in the same sense that division here and multiplication here are inverse operations. To me, that's a stretch. But these books these days tend to try to get you some esoteric way to think about this. Let's just go on and do it. The fundamental theorem of calculus states that the limit processes used to define the derivative and the definite integral preserve that inverse relationship. Okay? And here's the fundamental theorem of calculus. Most books will call this part 1. If a function f is continuous, okay, needs to be continuous, on some closed interval a to b, and capital F is the antiderivative of that little f. Remember, we did this back with indefinite integrals, antiderivatives, on that interval a to b. Then, the integral of f of x dx, this is fundamental theorem of calculus part 1, is the antiderivative, capital F, first evaluated at b, and subtract from that antiderivative evaluated at a. Okay? That's the fundamental theorem of calculus part 1. How you actually do those definite integrals without doing a Riemann sum, without doing a limit, without trying to make it into a geometric shape that you know the area of. This will give it to you. And boy, this is so much easier than any of the above. Okay? So the following guidelines can help you understand the fundamental theorem of calculus. Okay? Provided you can find an antiderivative of f. You know, there's no guarantee you can. There's some functions they call non-elementary functions. They don't have an antiderivative. We're not going to worry about those. Provided you can find the antiderivative of f, you now have a way to evaluate the definite integral without having to use a limit, without having to use a sum, just doing the integration. Okay? When applying the fundamental theorem of calculus, the notation shown below is convenient. If you have an integral, f of x dx, with limits on it, without limits on it, you just go and put the antiderivative plus c. Remember? That's how we were doing it earlier. Okay? Now, with limits on it, put that antiderivative. Don't put a plus c, but evaluate it between a and b in the same order, and it's always f, capital F of b minus capital F of a. That does it for you. Okay? So let's do this one. Evaluate the integral from 1 to 3 of x cubed dx. What's the antiderivative of x cubed? You know, it's been a long time since we did those.
1 over the n over 3x.
Say that again.
The antiderivative.
Antiderivative of x cubed.
Oh, shucks. X to the 4 over 3.
Over 4. Right?
Yeah.
Okay. And remember we said antiderivative, you're doing a reverse of what our derivative does. So they're inverse functions of each other. So that would be x over x to the 4th over 4. Okay? There it is. Now evaluate that first at 3. Woo! What is 3 to the 4th power? Anyone know? 3 to the 4th power. How about 3 squared? Anyone know that? 9. Now what's 9 squared?
You said 3 squared, I thought you were
81. So that would be 81 over 4 minus, and what's 1 to the 4th power? And that would be 1/4. 81 fourths minus 1/4 would be 80 fourths, which would be 80 over 4, which would be 20. Exactly. Okay? Now, notice, as I said, not necessary to use a constant integration. If you did, you would just add it here and subtract it there. So why mess with it? When you have a definite integral, leave off the plus g. Just evaluate the antiderivative between the two limits. Okay? Upper one minus the lower one. That's it. That's the fundamental theorem of calculus, part 1. So let's evaluate these. That first one. What would be, first, the antiderivative. Whoops, let me get my pen set up. We've been doing a lot of blah, blah, blah. Here we're actually going to do something. Okay? Antiderivative of x squared. X cubed over 3 minus what antiderivative of 3 dx is what? 3x. Perfect. And we're going to evaluate that from 1 to 2. Always do the upper one first. So let's do that. What's 2 cubed? 2 cubed? 8 thirds minus 3 times 2 is? Anybody? Evaluate this part at 2. 3 times 2 is? 6. Okay. Now we do minus the same evaluation with 1. So 1 cubed is 1. Over 3 would be 1/3. Now here we do a minus of a minus, which makes a plus. Now, A, if you need to write out as many steps as necessary to see why this is true, write them out. I'm doing it shorthand because I don't have a lot of room here. But take as many steps as you need. So evaluate 3x when x equal 1. What would that be? 3 times 1. 3 times 1. 3! Good deal. Okay? Now let's combine what we've got. Okay? 8 thirds minus 1/3 would be 7 thirds minus 3. Okay? Well, how many thirds is 3? How many thirds is 3? Okay? If I had 3, I think in terms of food. If I had 3 pieces here and divided each one into thirds, how many thirds would I have? 9, okay? I think with my stomach, okay? So that'd be minus 9 thirds, right? 9 thirds is 3, right? And what does that give you? 7 thirds minus 9 thirds. It's not that hard. Negative 2 thirds. Perfect. Okay. Can you have negative answers? Sure you can. All right. Uh-oh. How in the world do we do that B? What would be your first step? Say again? I'm sorry?
So that would be, you just rewrite it as 3 times x to the 1/2.
To the 1/2 power. Perfect. dx. Now do your integration. Actually, I wish I'd have taken the 3 out here because that's legal too, isn't it? So let's do it. Okay, that was easy enough. You have to write everything again. I don't have to. Okay. So that'd be 3 times antiderivative of x to the 1/2. X to the 3/2 over 3/2, which is the same as times 2/3, right? Right? Okay. Now, and we're going to evaluate that from 1 to 4. I like that. Before I do that, I'm going to notice that my 3's cancel out. Oh, wow. They divide away. Okay. So that leaves me with 2 times, what is the square root? Now you plug in the 4 first. Square root of 4 is?
16.
Square root of 4?
Oh, 2.
It's 2. And 2 cubed is? 2 cubed is?
4.
2 cubed is? 8. All right, good deal. Harder than I thought. Okay. Minus, see, I pulled the 2 on the outside, just doing the minus here. The square root of 1 is? Square root of 1 is? 1. And 1 cubed is? 1. All right, minus 1. Okay. So this will be 2 times 7 is 14. Good deal. All right. Oh, boy. What's the antiderivative of secant squared? We remember this. Oh, yes, we do. Antiderivative of secant squared. If you don't remember, you can just go to the front inside cover of your book and do number 14. It's tangent. Okay. That would be tangent x, and you evaluate that from 0 to pi fourths. Guess what that would be? Which one do you do first? The upper one. What's tangent of pi fourths? Anyone remember? Tangent of pi fourths? Oh, I'm going to have to talk with your trig instructor. Okay. Tangent of pi fourths? Okay. Anyone remember what the tangent, the sine of pi fourths was? Please say yes. Yeah. Square root of 2 over 2, is that what I heard? How about cosine of pi fourths? Square root of 2 over 2, and guess what tangent is? 1, so sine divided by cosine, they're the same, so that's 1. And what's tangent of 0? Second? 0. 1 minus 0 is 1. There we have it. Okay, so can y'all remember this? Minus 2/3, 14, and 1. Let's see how the book did them. Any questions before I delete them? Anybody? Okay. The first one. The antiderivative of x squared is x cubed over 3. Antiderivative of minus 3 is minus 3x. Evaluate this between 1 and 2. 2 on top, 1 on the bottom. Do the top one first. And what you get there is 2 cubed is 8/3 minus 2 times 3 is 6. Then subtract doing the minus. And like I said, if this helps to separate them out like this and do that, do it. Okay? And then 1 cubed is 1/3, so that gives you a 1/3 minus 3 times 1 is 3. But that's in parentheses, so if you clear the parentheses, distribute the minus sign, what you get, oh, they don't even show how you do it. They got minus 2/3, which is exactly what we got, right? Remember? Okay. They went to great extent to put that first step in and then skipped all the other steps and wrote the answer down. Okay. Now, the next one, they did the same thing you did. They first wrote it, they pulled the 3 on the outside, and they wrote the square root of x to be x to the 1/2. Then they did the integral of that. And what was the antiderivative of x to the 1/2? Wasn't that long ago you did it. What was it? Antiderivative of x to the 1/2. How does it start anyway?
It's x to the 3/2.
Okay, x to the 3/2, and then you divide by 3/2, which is the same as multiplying by 2/3. So that gives you 3 in the front, and they divided by the 3/2, and wrote x to the 3/2. And boy, that is so awkward a way to try to do this. Let's see what they do on the next step. Next step, they magically do something very different. Here's what happens. The divided by 3/2 is the same as multiplying by 2/3. The 3 will cancel out, so you have 2 times 4 raised to the 3/2 power minus 2 times 1 raised to the 3/2 power. Okay? Now, if the denominator here is 2, that means the square root. If that's a perfect square, do that first and then cube it. Otherwise, you're cubing a big number, getting a huge number, and then taking the square root of a huge number. So much easier to take the square root of a small number, getting a smaller number, and then cubing a smaller number. I like to do it that way. So it's 2, but you could have pulled the 2 on the outside here, but this is fine. And they just said 14. Okay. The cube root of the square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. Minus the cube root of the square root of 1 is 1. 1 cubed is 1. 1 times 2 is 2. 16 minus 2 is 4. Okay. They go to great lengths to show every step to begin with and skip a bunch of steps at the end. All right, the third one. The antiderivative of secant squared is tangent. Evaluate that between pi/4 and 0, and you get 1 minus 0, which is 1. So, yep, we got them right. Any questions on those? Okay. Now, that was example, hopefully, 1. Yeah. They are skipping example 2, 3, before they get to mean value. So let's go back. And do example 2 here. Now, example 2 is somewhat similar to what we did before, but I'm going to write it down first, and then we're going to do some scratch work on the side. Here's what your integral is. The integral from 0 to 2 of the absolute value of 2x minus 1 dx. That to me is sort of a big boo hiss. Okay? Now, and here's why. Even though the x's, and by the way, this stands for x equals 0, x equals 2. You're evaluating between those two values. Even though these are both positive numbers, that doesn't guarantee that what's in here is positive. So what we have to do, anytime you have an absolute value, because guess what? An absolute value function, even though it's continuous, is not differentiable because it has that point, remember? It's not a smooth curve. To be differentiable, it has to be smooth and continuous. This is not smooth. So here's what we do. Here's what I do. I go off to the side here and define what the absolute value of 2x minus 1 is. And it's just like we did it before. It is minus 2x minus 1 anytime 2x minus 1 is less than 0, and it's positive 2x minus 1 anytime 2x minus 1 is greater than 0, or equal. You can put the equal there. Either place, it doesn't matter. That's how we define absolute value. Whatever's on the inside, anytime that's negative, you do the opposite of it. Anytime it's positive, you just take its value, right? That's what absolute value means, right? Now, here's the key, folks. This thing right over here. Those are the same inequalities. We want to know, let's basically say where that is equal to 0. That's going to be the dividing line. So let's take that. 2x minus 1 equals 0. Tell me what x value that'll be. That'll be 1/2. Add 1 to both sides, and that gives you 2x is equal to 1, divide by 2, and you get x equal 1/2. So we're going to split this to be the integral from 0 to 1/2 of that upper one, this one here, because there it's less than 0, right? Between 0 and 1/2, this thing is negative. Now, what is minus 2x minus 1? Isn't that the same as 1 minus 2x? Yeah or nay? Yeah, okay. So that'll be dx. There's your first one. And then the second part is plus integral from where to where? You covered from 0 to 1/2, so where does this one go? From 1/2 to 2. And then you just use it like this, 2x minus 1 dx. So now let's do each of those separately. What's the antiderivative of 1? Second? X. What's the antiderivative of 2x? X squared. And you evaluate that one between 0 and 1/2. Plus antiderivative of 2. 2x, I mean. X squared. Antiderivative of minus 1 is? Second? Minus x. Okay? Evaluate that from 1/2 to 2. Okay? Let's do the first one. 1/2. And what's 1/2 squared? 1/4. I'll do the second part. 0 minus 0 equals 0. Okay, I did that one for you because it was hard. Okay? So there's your first part. Plus, now this time we're evaluating at 2. What's 2 squared? 4 minus 2 minus, okay, 1/2 squared is 1/4 minus a minus, which is plus 1/2. Okay? Now, because those parentheses really aren't doing us any good, I'm going to erase them because they're preceded by a plus sign, so it really doesn't matter. Now, let's see what we've got here. 1/2 plus 1/2 is 1. Minus 1/2 minus 1/4 minus 1/4 is minus 1/2. And then what we have left over is plus 2. So that's going to be 3 minus 1/2, which is 3 minus 1/2. Not that hard. 2.5. Or probably the book's going to write it as 5/2. Okay. That's my guess. What does the book get? 5/2. Okay. Now, see how that worked? Any questions on that? They do show the picture in the book. The absolute value is like this. The little bit that's over here has a positive value. The big bit over here has a positive value. And you add them together and you get 5/2. All right. Now, we could have done that using triangles. Would you rather have done it that way? Please say no. Good. Excellent. All right. Let's do example 3. Can I erase? May I erase? Okay. Example 3. Find the area of the region bounded by the graph of y is equal to 2x squared minus 3x plus 2. The x-axis and the vertical lines, x equals 0, okay, x-axis, and the vertical lines, x equals 0 to x equal 2. All right, now, what they did, they showed the graph in the book, and they showed that this was indeed a parabola, which it is, obviously, right? What's not obvious about it is whether that's always positive. It's always above the x-axis. They showed it in the book, and sure enough it is. Okay? If you have a graphing calculator, you can punch it in there and see if it's above the x-axis. If it is, fine. We'll just integrate. Okay? Because that's what finding the area bounded by those regions. Okay? And so the area is equal to the integral from where to where? X is going from 0 to 2. And you know you use those x's because that's what your dx is going to be out here. And then what's the function you put in here? 2x squared minus 3x plus 2. That's the function values that you're doing of all those little rectangles that you're adding together, summing up with your integral here. Okay? But they have incrementally small thicknesses. Delta x's becomes a dx. Okay. What's the antiderivative of 2x squared? 2x cubed over 3. Excellent. Minus, what's the antiderivative of 3x? Help me, somebody. Antiderivative of 3x. 3x squared over 2. All right. Plus, and what's the antiderivative of 2? 2x. All right, good deal. Evaluated from 0 to 2. All right, so what we're going to do is plug in the 2 first. It's the upper one. And what's 2 cubed? 8 times 2 is 16 thirds minus 2 squared is 4 times 3 is 12 over 2 is 6. Plus 2 times 2 is 4. And I'll do the minuses, okay? 0 minus 0 minus 0, okay? I did that part because it was hard, okay? Now, what does this add to? Well, these two add to minus 2, so that would be 16 thirds minus 2. But let's write that minus 2 in terms of thirds. 16 thirds. And how many thirds is 2? 6 thirds. Because 6 divided by 3 is 2. So this will be 16 thirds minus 6 thirds is 10 thirds. That's what we got. How'd the book do? Good, they got it right. Good for them. Any questions on that? Now, if this had dipped down below the x-axis, you couldn't find the area this way. Because then the part below the x-axis would be subtracting off the other one. You get too small of a number. But, so it is a good idea to make sure the graph does stay above the x-axis. This one did. All right. Now I think we're ready for, I'm ready for bed. Okay. I had a really long, hard weekend, and I haven't caught up since then. So, all right. Mean value theorem for integrals. I don't know if you remember the mean value theorem before, but we're going to now do it for integrals. Okay? You saw that the area of a region under a curve is greater than the area of the inscribed rectangle and less than the area of the circumscribed rectangle. Okay? All right. If you were to, if that's your curve and you do the area, the rectangle is completely under that curve, that would be a rectangle that went right along from the minimum value here to there. That would be that area. And the circumscribed rectangle would be going from the maximum value here down. That would be the circumscribed rectangle. The area under the curve would be in between those two areas. I wish I'd drawn what they were talking about. Okay? The mean value theorem for integrals states that somewhere between the inscribed and the circumscribed rectangle, there has to be a rectangle whose area is precisely equal to the area under the curve. That's what they've drawn here. The area under the little blue rectangle here is exactly the same as the pink area underneath the curve. In other words, the area that's totally blue here is about, in fact, they say is exactly equal to that area. Okay. Now, that's in general what the mean value theorem says. If you're taking the minimum value here, drawing the rectangle here, that would have been the inscribed rectangle, and the maximum value here, drawing the rectangle there, that would have been the superscribed rectangle, circumscribed rectangle, and somewhere in between those two is your rectangle that has exactly the same area. Okay? Now, that means there's some C in between A and B. Remember, F has to be a continuous function. They didn't say that here, but I'm saying it now. If F is a continuous function, and F of A is not equal to F of B, okay? That doesn't quite pan out either. The minimum of F, there's got to be some value C in between A and B such that the area of the rectangle that's represented by B minus A is the length, F of C is the height, so F of C times B minus A is exactly the same as the integral under the curve. Okay? Now, that's just what mean value theorem says. Right at first glance, it doesn't seem all that useful. It's just an observation. Yeah, it's got to be. Okay? Now, here's how they write it formally. It still probably isn't very practical, but formally. If F is continuous, there it has. They didn't say it earlier, now they're saying. If F is continuous on a closed interval, A to B, then there exists some number C on the closed interval A to B, some number C on the closed interval A to B, such that the integral, the total area of that function between A and B, f of x dx, the area under there is equal to that function evaluated at C times the length A to B, A minus B, B minus A. Ooh. Okay. Now, that's all they do with it. They don't use it, they just state it. Oh, I'm sorry. That's all they do. I'm sorry, even in the book. I looked at the next page. All right. Now that leads to what we're going to do next. Okay? And here's what that is. To find the average value of a function. Basically what we're going to say, that's that value alpha c. The average value of the function will be what the mean value function called alpha c. All you do is integrate the function, divide by the B minus A. Okay? And that's exactly what this says. The value alpha C, given by the mean value function, mean value for integrals, is called the average value of F on the interval A to B. So here's the definition of it. If F is integrable on a closed interval, when it says integrable, that means it's continuous. So if F is integrable on the closed interval A to B, then the average value of F on that interval is 1 over B minus A. This is your alpha C, is 1 over B minus A times the integral of alpha dx from A to B. Okay? Now, in this figure, the area of the region of the graph of F is equal to the area of the rectangle whose height is that average value. Now, this is where I was afraid they were going to be stating something they shouldn't have. Here your F of A is here, and your F of B is here, and they are different. What if they had been exactly the same here and done this kind of stuff and come up there? This still works, okay? It's not like the Rolle's theorem before. That isn't involved here. It's just that if this F is continuous between A and B, there's some value. Now, in this case, we don't even care what C is. C was some number between A and B. It could be this number, it could be that number, or it could be that number. Because there's 3 different places it has a value that is that. But whatever the average value is, irrespective of what the C value is, that's not important anymore. It's just 1 over B minus A times that number. Okay? That's all. You don't even need to identify what the C is. Because this has any one of 3 C's you could have used there. You could imagine functions that could have a large number of C's. It doesn't matter. You're wanting only the average value of the function, and that's F of C, whatever C is, you don't care, and that's your 1 over B minus A times the integral. Okay. To see why the average value of F is defined that way, partition A to B into n subintervals of equal width. We thought we were through with this, didn't we? The delta x is B minus A over n. If C sub I is any point on the ith subinterval, then the arithmetic average, or the mean of the function values at the C's is, now, I kind of regret they use A sub n. They did it because it's the arithmetic average, or the mean. They've already used A, so why couldn't they use something else? Mu, for instance, that's what they use in statistics. I would have said mu sub n. They did A sub n. Remember, that has nothing to do with that A. A sub n, that's the average, is add up all those L sub C, so you have the n subintervals here, and pick C as any point in that n subinterval. The arithmetic means of those would be the C's are down here, alpha C would be up here, the average would be alpha C1 plus alpha C2 plus alpha C3 all the way up alpha Cn. You have n terms there, divide by n, that's the average. Just like your grades. You have 3 grades, add them together, divide by 3, you get your average. Okay? That's all this is saying. This A has nothing to do with that A. This is an average A. That's your initial endpoint. I wish I'd have used different letters. Okay. By writing the sum using some summation notation, which is really what I love doing, and dividing by B minus A, you can then write the average as, now this again is the average. It's the summation, is 1 over n times the summation of all your alpha, summation of I equal 1 to n of alpha C sub I. Okay? Now, they do something strange here. Multiply and divide by B minus A. Alright? The just a reminder here, your delta x is b minus a over n. So your delta x is b minus a over n. So here's your b minus a over n. You multiply by that. Pull your 1 over b minus a out front and pull your n inside to switch those two. This now is your delta x, and there is your summation. This becomes your integral f of x dx. Okay? So that's how they justify it, and it's perfectly fine. I never go back to those if I can help it. Okay. Finally, we're taking the limit as n approaches infinity, produces the average value of interval a to b as in the definition. Okay. In figure 432, notice that the area of the region under the graph of f is equal, or at least it looks like it is, to the area of the rectangle whose height is the average value. Now this is the same graph they showed before, but now they have reason to show it. Okay. The area under the blue area here is the same as the total of the pink area here. In other words, this is a little bit less than that, but this is a little bit more than that. They average out to be the same. Okay? It's not a proof, but it just gives you a warm and fuzzy that it's right. So let's do it. Find the average value of f of x equal 3x squared minus 2x on the interval 1 to 4. Guess what we would do first? We're looking for average value of f. You know what? To keep from calling that an a, I'll call it an a because we don't have a's in here anymore. We'll call it a's, not a sub n. Here's what I want to call it. F bar. Average value of f. Why not? I mean, that's what usually we use for average value is a bar over it. Okay? What would that be? Anyone remember the definition? 1 over b minus a times the integral from a to, okay, they are using a. I'm glad I used f bar here. A to b of f of x dx. Okay? In our problem, what's your a? What's your b? What's your b first? 4 minus, what's your a? 1, evaluated from, in the integral from 1 to 4 of, what's your f? 3x squared minus 2x dx. That's it. What's 4 minus 1? Okay, so it's 1/3. And can we do the antiderivative of 3x squared?
Yes,
X cubed minus x squared, evaluated from 1 to 4. This will be 1/3 times, what's 4 cubed? Ooh, 64. Minus 4 squared, 16. Minus, what's 1 squared? 1 cubed? Minus a minus is a plus. 1 squared? 1. Okay? Obviously, those two add to 0. And 64 minus 16 is? 48. And 48/3 is? Say again? 15? Is that what I heard? Or 16? 16. Okay, good. I can't hear well, so I want to make sure you said the right number. 16. And look at that. Wow. We're going to see how they did. The same answer they got. Okay. Any questions on that? Average value of a function. All right, to erase. All right. So let's see how they did it. My goodness, my throat is dry as crazy. I drank something at the break. Average value is 1 over b minus a times the integral from a to b of f of x dx. Our b is 4, our a is 1, so it's 1 over 4 minus 1, the integral from 1 to 4, and our f function is 3x squared plus minus 2x dx. That'd be 1 over 3 times antiderivative of 3x squared is x cubed minus the antiderivative of x squared of 2x is x squared. Evaluate those between 1 and 4, and you get 1/3, 64 minus 16 minus 1 minus 1, or however you want to do that. But you get 48/3, which is 16. All right. There's the graph of it. And this is going from, they don't show the figure here, but yeah, that's going from 1,1 to 430. I didn't plug those in, but you can if you want to. When x equals 1, this is 3 minus 2 is 1, so that value is 1 at 1, 1. And when x equals 4, whew, big number. 48 minus 8, which is 40. Way up there. So they compressed the y scale, expanded the x scale. So anyway, there's the graph of that parabola, that portion of the parabola. Now the good news here is you didn't go below 0 here. You could have, but they stopped you before you got there. Okay? And then, achy, staring into the brightness here. Okay? And they say the average value is 16, which would be 16 times 4, there's your 48, and we already got the area under there was 48. So there's what we got. No, I'm sorry. Yeah, average value of the function was 16, and then if you multiply 16 times 4 is 48, and that's the whole area under there. 48 times 3, yeah. There, that's the area under there, 48. All right, that was example 4. They're skipping example 5, and example 5 is worthy of being skipped. It's a very practical problem to some extent, but it's a real pain in the neck to do. Okay? And it gives some pretty good insight. But like I said, it's a real pain in the neck to do. Okay, I don't think I can hold this up much very long. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, s of x, in meters per second, can be modeled this way. Okay, this is just a model. It's not exact. I would not expect these to be sharp corners here, but this is the best way they have of modeling it. Now, I can't hold that up any longer, but you see all of those are straight lines. Okay? Now, the x's are to the first power. Probably if you had done a little bit larger exponent or allowed the exponents to float, you could have had a much more rounded curve, but then that would have been hard to evaluate. Okay? And let me explain to you, at least in a general way, why the speed of sound changes. Okay? As you go up in altitude, the speed of sound for the first 11.5 meters per, meters. No, kilometers. X is in kilometers. I thought then that's not very much. 11.5 kilometers, which is about 6.5 to 7 miles. The speed of sound actually is decreasing. Now, why would that be decreasing? There's basically kind of two reasons. One, and it's not real clear why, but the spacing between air molecules is gradually getting larger, but also the temperature is typically going down. And when you go down in temperature, the speed of sound decreases. So that's probably, the temperature is probably the major thing for that first 11.5 kilometers up you go. Okay? Then they say it's constant for about the next 10.5 kilometers at 295. It just sits there at 295, constant for those 10.5 kilometers. Then it actually increases slightly. Okay? Now I can't get into all the reasons here, but I bet you if you did a temperature graph, you would see some of the same similarities, but you also have the distance between molecules too. So all I can give you is a rough thing. And then it increases even more sharply for the next period of kilometers, and then falls pretty sharply after that. Okay. Says here that what is the average speed of sound over the interval 0 to 80? Well, you have to do the integral from each of those pieces there, 0 to 11.5 of that first linear function, then just your constant function between 11.5 and 22, another linear function between 22 and 32, another one between 32 and 50, and yet another one between 50 and 80. So you integrate your S of x, speed of sound, which is given by that, over that whole interval, but you have to do 5 different integrals to get that, add those two up, and then divide by 80. And it gives you about 308 meters per second. Okay? Which is not far off from what most of them are. It sort of fits right in the middle of the first interval. The second and third ones are below that, but coming up to that, the third one passes that and goes higher, and then the fourth or the fifth one drops down, and it's right about the middle of that. So anyway, they don't do it on the PowerPoint. I'm not going to do it either. You can do that on your own. It's not a hard process to do. It's just tedious with the numbers, the fractions, the decimals, evaluations. There, it just gets tedious. So let's move on to the second fundamental theorem of calculus. Some books will call this fundamental theorem of calculus part 2. This one calls it second fundamental theorem. Earlier, you saw that the definite integral of f on an interval a to b was defined using a constant b as the upper limit of integration and x is the variable of integration. Now we're going to do something rather bizarre, but it's legal. A slightly different situation may arise when the variable x is used as the upper limit rather than b. But now you can't use x as the variable of integration. But remember, that was a dummy variable anyway. So you can use anything you want to there. T, stickman, whatever you want to use there, you can put that as your thing of integration because it's a definite integral. So to avoid the confusion of using x in two different ways, t is temporarily used as a variable of integration, or anything else. It doesn't really matter. Remember that the definite integral is not a function of its variable of integration. It's a number. A definite integral is just a number, a value. It's not a function. Okay. So here's what we do. The definite integral is a number. We do the integral from a to b, f of x dx. X is just a dummy variable. F is some function of some variable x. And when you do the antiderivative of this, evaluate between those two, you just get a number. You just get a number. Okay? Now, if you do it this way, that your capital F of x, now that's a variable function of x. So you replace the upper limit b with x, and you go from a to x, and then in here, just put a dummy variable, t. Okay? S, it doesn't matter what you do, because when you take the antiderivative of this, you get capital F of x, right? Capital F of t. Evaluate x equal t, you get f of x equal a. F of a is, doesn't show up now as correct, but you would think that would have a minus f of a in it. Capital F. If that is indeed the antiderivative. I guess now they're saying it's not. Okay, not quite. Within a constant being the antiderivative. So, let's evaluate this function at these 5 values. Okay? One way to do that is plug them in one at a time. If you put 0 in there, what's your answer? 0, because anything, okay, you do that. If you put pi 6, then you have to do what's the antiderivative of cosine x? Sine x, okay? And sine of pi 6 will give you an answer. Because sine of 0 is 0. Okay, you could do that and plug each value in and then do the integral over and over and over. But easier than that is what they just showed us. And what is the antiderivative of that? It would be sine t, right? Evaluated from 0 to x. Well, that would be sine x minus sine of 0. But what is the sine of 0? Anybody? 0. So this is just sine x. So then just plug these in. At 0, sine x is 0. At x equal pi 6, sine pi 6 is equal to 1/2. At pi 4th, sine of pi 4th is what? Anyone remember? Root 2 over 2. We already had that today. At x equal pi 3rds, sine of pi 3rds is equal to forgot the easy way to do it, don't you? Huh? Easy way to do it. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, yeah. And at x equal pi halves. That only works with these special angles here. 0, pi 6, pi 4ths, pi 3rds, and pi halves. What's sine of pi halves? Say again? 1, which is square root of 4 over 2. Square root of 4 is 2 over 2 is 1. So yeah, that works. Okay, so do the integral first and then just plug in the values. Otherwise, you have to plug in the value for x at every one, do the integral, which comes out the same, but then it's just a lot longer to do it that way. That's the use of the second fundamental theorem of calculus. So let me erase what I did. And let's see how they did it. Okay? You could evaluate 5 different integrals, definite integrals, 1 for each given upper limit. However, it's much simpler to fix the x as a constant temporarily to obtain, that'd be the sine of t between 0 and x, and that's just going to be sine x minus sine 0, which is, of course, sine x. Because sine of 0 is 0. Now, evaluate that answer, the sine x, at each of the values. At sine x equals 0, that's 0. Sine x at pi 6, the area is 1/2. At pi 4, it's root 2 over 2. At pi 3rd, it's root 3 over 2. At pi half, you have exactly 1. Amazing. Okay? My stomach is growling like crazy. You can think of the function f of x as accumulating the area under the curve of alpha t is equal cosine t from t equals 0 to t equals x. That's what that figure was showing. Here, you have nothing under there, but as you move out here, let t increase, okay? Let t increase, then you have a little bit more area, a little bit more area, a little bit more area, finally the whole curve under there, which happens to be 1. Okay. So that's the accumulation of the area as you let x vary from 0 to 1. Okay. It's on the t-axis, but it's x is changing. Okay. For x equals 0, the area is 0. Alpha 0 is 0. For x equals pi halves, alpha pi halves is 1. That's the entire interval 0 to pi halves. That interpretation of an integral as an accumulation function is used often in applications of integration. They say. I don't usually use it very often at all, but they will use it some. Now, in example 6 that we just did, note that the derivative of capital F is the original integrand. I think we had noted that before, so get this, folks. D by dx of capital F is d by dx of sine x in that problem we just had. And what's the derivative of sine? Derivative of sine? Cosine. But if you did d by dx of this right here was this thing, okay, remember, this was that, so that's putting that in its place, and then you have d by dx of the integral of cosine. Well, just like we said, they're inverse functions of each other, so if you integrate a function, cosine x, then take the derivative of that integral, you get cosine x, okay? The result is generalized in the following theorem, and this is what we mean by the second fundamental theorem of calculus. If f is continuous, now f has to be continuous, okay, on an open interval I containing a, okay, then for every x, for every x in the interval, d by dx of the integral of alpha t dt, integral from a to x, of alpha t dt is alpha of x. Take this function, evaluate it at that value. Okay? This value is also the value you're taking the derivative with respect to. Not that one, but this one. Okay? Now, so in other words, start with the function, integrate it, differentiate it, you wind up with the function. Okay? Wind up with the same function. Okay. The variable changes, but that's all right, just the function is the same. Now, using the area model for definite integrals, the approximation of f times dx, f of x times delta x, is approximately the integral from x to x plus delta x. So in other words, from x to a little bit further than x, delta x, of f of t dt, that integral should be just this f of x times the delta x. Now that's an approximation. It's not exact, it's an approximation. That can be viewed as saying that the area of the rectangle of height f of x, okay, and width delta x is approximately equal to the area of the region lying between x and x plus delta x, okay? So this is an approximation, it's not exact. If you know the f of x at some point, and you know the delta x here, f of x times delta x, that's this thing, is approximately, not the same, but close to the integral of f of x dx. F of t, f of t dx, the integral f of t dx, where t is going from x to x plus delta x. So this is the actual, the pink is the actual, the blue is the approximate area, so they're pretty close. And of course, as your delta x is smaller and smaller, that gets closer and closer to being exactly the same. Okay. All right. Example 7. Okay. Don't overthink this one. Just do what we just learned here. What would this answer be? Can you just write it down? Perfect. Perfect. That's all you do. If you're taking derivative with respect to x of an integral going from 0 to x of whatever your dummy variable is in here, then the derivative of an integral is just the function itself evaluated at that value x. So it's square root of x squared plus 1. Nothing more to do. There's no additional steps. You just do that. Okay? And that's, note that f of t is equal to square root of t squared plus 1 is continuous on the entire number line. Okay? It is, okay? Continuous on the entire number line. It's not smooth, but it's continuous. Okay? Nothing said it had to be smooth. It is continuous. But going from 0 to x, it's not only continuous, but it is smooth from there. Okay? Because it goes from 1 to, and just keeps on going. So it's continuous on the real number line. So since it is, you can use second fundamental theorem of calculus and just plug and chug. And that's eyes are just stinging. So you can write the second fundamental of calculus. D by dx of that is just square root of x squared plus 1. So I guess we really should have said all those things about being continuous on the interval of interest, and that was fine. All right. They're skipping example 8. So let's us do 8. Word. This happened Monday too, I think. I don't know if staring at the screen or the board or something is just making my eyes. Actually, now I think about it. Ever since I had the cataract changed in this eye, now neither eye will focus because the cataract, the lens they put in is fixed. Your old lens, you know, your muscles did this to it and you tried to adjust. That's how you could see varying distances. But when they take those out, put them in, this one sees close, this one sees far. But to see my computer or the board, those are different distances. So this helps me read the book better, but it doesn't help in distance. So I think what's happening, my muscles in there are doing this to those lenses, and they can't move them, and they're just straining. Now, I don't know if that's happening, but that's what it feels like. I'm supposed to get some glasses at the end of the month that are going to adjust for all that. And they won't be just fixed lenses, they'll be progressive. So hopefully I'll be through with that. Yeah. So let's do example 8. Let's go the other way. Find the derivative of capital F of x when capital F of x is the integral from pi halves to x cubed. I forgot to open the door. I'm sorry, Dr. Bryant. Okay. Of cosine t dt. All right. Now that looks a lot like this one, with one major exception. That's an x cubed, not an x. If that was an x, we could write down the answer. Because it doesn't have to be a 0 down here. That could be anything. Remember, the original first had an a down there. That could be any constant. The problem here is that's x cubed. Okay? And we want to get the derivative of that. Now, this is something we're going to do a little bit later, but I think you'll still see it's a legal move. Let's first say, are you okay with this? Let u equal x cubed. Just do a substitution, right? Now, then I think it's quite, well, without introducing the F in here yet, or maybe I should. Okay, let's just do with this. Then this expression here becomes the integral from pi halves to u cosine t dt. Now, if what we're looking for was the derivative of that, what would the derivative of this be? We just did it up here, or something very similar. That would be cosine u, right? But u is x cubed. To get what we wanted was derivative of this thing with respect to x. So what we've still got to do is, I'm going to move my equal signs over a little bit and do a du dx. And that would then be exactly what we've got here, right? What is du dx? Anybody? If u is x cubed, what's du dx? It's pretty easy. What? If u is x cubed, what's du dx? 3, second? 3x squared. So then the du dx, so d by dx of f of x will equal du dx of d by du. So this would be 3x squared cosine And now we can put the x back in. Cosine x cubed. Okay. Because the cosine u didn't change, so that u was x cubed. So it's, they wrote it backwards or different in the book. They wrote cosine x cubed times 3x squared. Okay. All right. I can't for the life of me see why they did the stuff at the bottom, but we'll move on. All right. Next we have, okay. Oh, is it time? Oh, sadly it is, isn't it? Okay. We'll start next time at net change theorem. But before you go, I know you would be very upset with me if you had the weekend ahead of you and no calculus to do. So let's, oh, we almost finished. I mean, we're that close to finishing. Homework exercises due either 5 or 7. They're both at Calc Chat. This is on 4.4, 292, starting there. Do any of the odds 9 through 35. They're all at Calc Chat. 19's at Calc View. Do either 37 or 39. They're both at Calc Chat. 37's at Calc View. Do any of the odds 41 to 45. They're all at Calc Chat. 43's at Calc View. Do any of the odds 47 to 51. They're all at Calc Chat. 47's at Calc View. Do any of the odds 53 to 57. They're all at Calc Chat. 53's at Calc View. Do any of the, let's see. Do either 59 or 61. They're both at Calc Chat. 61 is referring to something called Buffin's needle experiment. You might check and see who Buffin was to see if that's somebody you might want to write about. And why did he do the experiment, what it came to. 63 is at both Calc Chat and Calc View. 65's at Calc Chat. And 67's at Calc Chat. Do any of the odds 69 to 73, they're all at Calc Chat. 71's at Calc View. Any of the odds 75 to 79, they're all at Calc Chat. 75's at Calc View. 81 to 85, they're all at Calc Chat. 87 is a graphical analysis. It should be at Calc Chat. 89 is a water flow problem. It's a Calc Chat. 91 is a velocity problem. It's a Calc Chat. Excuse me. Okay. 93 through 97, they're all at Calc Chat. 93 is at Calc View. And exploring concepts 99 or 91 should both be at Calc Chat. I think you can stop somewhere there, and we will do the rest of those next time.
So we got 2 more tests to do. We only got 2 more weeks to play.
Okay. Yeah. Let me address that right now. We've got integration by substitution is 4.5. That's a fairly sort of long, but it's a fairly quick section. And then that's it for this one. Now, I think what we'll do then is chapter 5 will just cover the high points in it, because we don't have to go back and reinvent the wheel. What chapter 5 is dealing with is basically dealing with functions that are logarithmic, exponential, and it says other transcendental function. We're only going to deal with the log and the and exponential. So we'll just breeze through most of that, and what I'll do is then your final exam will be chapter 4 and then a little bit of 5. Okay, so it'll be, that's how we'll cover that.
That's my district.
All right, good deal.
Thank you.
Thank you. Thank you. Give me plenty of grade this weekend. Thank you very much. Okay.